Have you ever noticed that your room only gets messier over time? Well, guess what? Everything in the universe works the same way. Things only tend to get more disordered on their own. For instance, let's look at this video. Can you tell which side is played forward and which is played backward?
Oh yeah, that's easy. The balloon is exploding.
But did you realize that things got more disordered during the process? The molecules of water went from a nicely organized balloon shape to random droplets flying out in every direction. And how about this one? Which one is played forward?
The right one. Everybody knows that orange juice doesn't assemble itself back into the pulp of an orange.
Alright, how about this last example then? A chemical reaction involving three gases, nitrogen, hydrogen and ammonia.
This one is harder. Are nitrogen and hydrogen going to form ammonia, or is ammonia going to separate into hydrogen and nitrogen?
Well, this one is not so obvious, but there is something that can give us the answer to these three situations. The reactions resulted in increased disorder, and in physics we use the notion of entropy to represent the fact that things tend to get more disordered over time. To put it simply, entropy is a measure of disorder.
But what do we mean exactly by disorder? Let's consider these three dice being randomly shaken, and let's look at the sum of the numbers on the dice. For example, if we freeze it right now, the sum is 4 plus 3, 7 plus 5, 12. We will call that the state of the system, and we'll use it to illustrate the notion of order. For example, if the three dice all show 1, then the state is 3. Note that there is only one way to obtain this state. All dice must be showing 1. By comparison, there are 3 possibilities to get into state 4. This state has less order than state 3 because the dice could be in any of these combinations and the state would still be 4. Now, there are 6 combinations of the dice that result in the state 5. This state has less order than the previous state because the dice could be in any of these 6 options and the state would still be 5. This example illustrates the notion of disorder. The more possibilities there are for a given state, and the more disordered that state is. Here's a plot that shows the number of combinations as a function of the state. There's a maximum for 10 and 11, which can each be achieved through 27 possible combinations. For example, this shows all the combinations that result in the state 10. This is the state of highest disorder.
Okay, so why is it useful?
Because it tells us how our experiment is more likely to evolve. In fact, as the dice change randomly, they're more likely to produce a 10 or an 11 than a 3 or an 18, because 10 or 11 are much more disordered states. You can see here that the state jumps a lot, but that's because we're only using 3 dice. Now, if you imagine that we have 100 of these dice, starting from the situation where they all show 1s, then this is how the state would evolve. The dice quickly move away from this very ordered state, and over time, the system naturally evolves towards a state of highest disorder.
Now, let's take a second look at the analogy with the tidiness of your room. The ordered state is the state in which every object is in its correct location. For each object that is not at the correct location, the room is more disordered. Just like our dice, there are a lot of configurations in which the room would be as disordered or equally messy. This would be the state of highest disorder, and over time, the room naturally tends to the state of highest disorder. Finally, let's see a practical example where entropy helps us understand the direction of a reaction. If you put some ice into a glass of water and leave it to sit, all the ice will melt. Of course you know this because the water is warmer than the ice. But what exactly is happening at the molecular level? The molecules in an ice cube are tightly packed together into a highly ordered lattice. Molecules inside a solid do move around, but not very much. This is why the ice is cold. Water is a liquid and has a higher entropy. Molecules in the liquid move around a lot more freely, which is what allows liquids to flow. Water molecules bounce off the ice molecules, giving them energy, and the ice begins to melt. Colder water has a much higher entropy than the warm water with ice. Although technically nothing physically prevents all the molecules from spontaneously forming an ice cube, at the molecular level this does not happen because of entropy. Just like our dice, there are many more ways for H2O molecules to arrange themselves in a glass of water than for the same molecules to arrange themselves into an ice cube. This is why heat always flows from a hot body to a colder body.
So now you can appreciate how entropy informs us about the evolution of physical processes. Entropy is a fundamental notion in science because it is a central pillar in thermodynamics, which allows us to understand everything from air conditioners to jet engines.
In fact, entropy helps us to understand the universe at all levels, from a simple system of 3 dice to billions of stars and galaxies. Entropy gives us the direction of the arrow of time. No matter what we're observing, we can be almost certain that the entropy of the universe is increasing.